Welcome everyone and Happy New Year. The AI for Net Zero webinar series is back in 2025 with more interesting talks from internal speakers of the AI for Net Zero project. But we are also targeting invitation of international speakers related to the theme. I'm Sarah Perez, international speaker, research associate at Elliott University, and I will be your chair today. Along with Professor Hamid and Shai. So the webinar series is designed to bring experts, innovators, and enthusiasts from both the artificial intelligence and sustainability domain, with the overarching goal to accelerate progress towards net zero targets. And the series aims to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. So we will delve into diverse applications of artificial intelligence across various domains, crucial for achieving net zero objectives, including energy, transport, environment, agricultural, and food system. Today, it's our pleasure to host Dr. Chenghong, who is a professor in smart energy system at the University of Bath. His research designs novel models and tools for planning and operating smart energy systems, including electricity, natural gas, heating, cooling, and transportation toward net zero. Professor Gu is a co-editor-in-chief for HIET Smart Grid, editor for HIEE Transaction on Power Systems, and he now serves as a member of the HIEE Committee for Power Economics and Markets. And he is co-chair of Super Gain Energy Network Hub, Markets and Regulation Working Group. Today he will talk about knowledge graph for data management in power systems. So please join me in welcoming him. Feel free to engage anytime in the discussion by writing your question and comments in the YouTube chat. I will host a Q&A at the end of the talk. So Dr. Gu, thanks for being here today, and the floor is yours.
Thank you so much, Sarah, for the introduction, and thank you for the invitation. So I'm very pleased to join this talk, and I'm delighted to present some preliminary work we have done at Bath on knowledge graph for data management in power systems. So this work is primarily done by PhD student Dr. Xinyuan He. So I'm really thanks to him. So digitalized power systems have seen a dramatic increase in the availability of diverse data sources. And this includes like traditional SCADA data, PMU, smart sensoring, and LiDAR technology, etc. So all providing real-time or close to real-time insights. So beyond traditional sources, new contributors like EV charging stations, smart meters, satellite imagery, weather forecasts are also enriching the data landscape. But however, in practice, each type of data is often siloed, so analyzed for specific applications without considering the big picture. This limits the potential value that we can get from this diverse data. So the real opportunity lies in integrating this multimodal data by bringing these diverse data sets together so we can uncover hidden insights and drive innovations far beyond the initial purpose of each data source. Open data and also effective data sharing are critical for the future of energy system. So Ofgem has developed a roadmap to establish energy data sharing infrastructure by 2028. So one key initiative is the digital spine feasibility study conducted by the University of Bath together with Arup and the Energy System Catapult. So this study explores the development of data sharing infrastructure specifically tailored for the energy sector. The effort is supported by the DESNES and focuses on creating a framework where data can be prepared, shared, and trusted. So as illustrated on the right-hand side, the proposed model revolves around connected nodes working collaboratively to foster trust and seamless data exchange, unlocking the valuable insights for a more efficient, sustainable energy system. So traditional data management faces many key challenges which hinder the full potential of data utilization in modern power systems. So first, there are diversified data formats, so that come in tabular formats like CSV files, PDF files, images, GIS, shape files, etc., making integration very complex. Secondly, so data silos are a persistent issue. Multiple stakeholders, such as generators, network operators, producers, and consumers, they often store data separately across different assets, generation systems, and low-carbon technologies, which limitate the collaboration. And also, there's inadequate interoperability. So many legacy systems rely on formats and protocols, preventing seamless communication between devices and systems. And also, finally, so limited data analytics capabilities remain a big barrier. So older systems are equivalent for predictive maintenance, data forecasting, optimization, so leaving significant insights untapped. So these challenges emphasize the need for modern, interoperable, and scalable data management system. So, for example, one of the UK's distribution system operator, National Electricity Distribution, they published their data. You can see there are around eight data sets published by the National Grid Electricity Distribution, and they are in very different formats like PDF, CSV, zip, GeoJSON, Excel, etc. So it's very difficult to integrate these different data sets together and to produce valuable insights into the conditions of the distributed networks. And also, I want to highlight, so this slide shows a project we are conducting for the National Grid electricity transmission. So it shows we are integrating data from various sources to create a comprehensive view. So we use network data in CSV format, location data from shape files for geographical context, failure logs from NER reports, and also lightning strike data from satellite images and industrial standards like SQS in PDF format. So combining these diverse data types give us a much richer understanding of the network. So what we really want is a unified data management framework to handle multimodal data and to interconnected data. And then we can explore advanced data applications and a semantic management tool to build an inclusive, flexible, and extensible platform for data management in smart energy systems. So this slide shows how we represent traditional power system as simple graphs. In the power grid, we have common components like substations, transmission lines. So we model this as nodes and edges. So that is kind of traditional power system graphs. So you can see on the left-hand side is the one-line diagram for the IEEE 5-bus system, and on the right-hand side, we can represent as a graph. So this graph only captures the physical connections, letting us analyze things like network connectivity, so checking for islanded or isolated sections or contingency scenarios, see what's going to happen if there's a component that fails. And we also can find also potential bottlenecks in the systems by running graph analysis. So importantly, this graph only shows the physical layout of the system. It doesn't include any operational data like power flows, so just connecting them. So then what is knowledge graph? So according to the definition from IBM, they defined the knowledge graph as networks of real-world entities like objects, events, or even abstract concepts, and the relationship between them. So technically, knowledge graph is a directed multi-graph. So we can break it down into triples which includes nodes, edges, and properties. So nodes are the things themselves, like people. Like for example, in this diagram, we have two people and one car. So the two people and one car, they can be represented as nodes. And the line connecting them are we call edges. So this represents the relationship between these nodes. And also for each node, they have different properties like edges, names, etc. So in short, the circles are things, lines are how they relate, and the little box are extra details about them. So knowledge graph can help computers make sense of information by understanding these connections and enabling everything from better search results to more intelligent AI. So this slide outlines our framework for building knowledge graph for power system operation and maintenance analysis. So our goal is to create knowledge graph that can help us better understand and manage power systems. So we can create this knowledge graph in two ways. So automatically from data or using knowledge, or a combination of the two. So this knowledge graph formation process results in the knowledge graph itself. So once we have the knowledge graph, we can query it for like entity recognition, identifying key components and their connections. So this gives us a knowledge graph explanation result. So finally, we validate the knowledge graph and use it for various applications, leading to the application output. So this could be anything from system planning, operation, and maintenance. So this framework will allow us to systematically build and use knowledge graph for more effective power system operation and planning. This slide details the steps we used to implement or develop our knowledge graph. So we choose Neo4j as the foundation tool. So Neo4j is a purpose-built graph database, so ideal for storing and querying interconnect data. So we also built a Python interface for easier interaction. So on the right-hand side, you can see that our process began with data collection, normally like Excel spreadsheet and a shapefile, etc. So we use a Python application to process these data sets, organizing it according to the CRM scheme, so which is a standard for power system information storing and exchange. And this structured data was then imported in our Neo4j data graph database. So finally, so we can use the Cipher, which is Neo4j's query language, to retrieve information from the graph, enabling us to develop further applications and also gain valuable insights from the data. So we used a national grid electricity distribution network as an example for developing the knowledge graph. So this slide shows data schema for our knowledge graph. So it's important to distinguish between ontology and a knowledge graph. So ontology provides the schema, the blueprint, while the knowledge graph contains all the actual data. So the ontology defines the types of things we are interested, like substations, transformer, and the floods, and how they are related. So knowledge graph then contains specific examples of these things and the connections. So we can see here, we have a visualization of ontology. So we have different nodes represent different concepts like risk, flood risks, substations, bus bars, transformers, circuits, etc. And also we have elevation, which is important for the flooding assessment of substations. And on the right-hand side, you can see some relationships which represent how these different nodes are connected. So we have 17 types of relations. So you have connected heads, etc. So this overview of the schema guides how we structure and populate our knowledge graph with the real data from national grid electricity distribution. So this slide is showing how we apply knowledge graph to the NGED system. So we are connecting data about various assets like bus bars, circuits, transformers, substations, and also disconnectors and circuit breakers. And we are also going to conduct a few queries to find the insights from the data. So as you can see, in NGED, they have four DNO regions, so they cover a large area of the UK system. And so in terms of data, so we are dealing with a large amount of data. So we have around 22,000 bus bars, 3,000 transformers, and we have also 21,000 circuits. So to connect the data, these types of data will allow us to perform powerful inquiries. So you can download all this data from the NGED open data portal. So I'm not going to discuss into details. So this first we design the bus bar node. So bus bar node, we assume they are one port just for connecting other assets. So you can see each blue dot in this diagram represent a bus bar. And for a specific bus bar, they have lots of property or attributes. They have element ID, so real ID, the GSP group, their bus bar ID, their name, code, etc. So all this information is from NGED data portal. And then we have transformer node. So each transformer is represented by a node in the system like this dark yellow dot. And also similarly for transformer node, so each node has ID, the GSP group, the license area, and also the tap ratio, the two nodes which they are connected to. And we have substation node. So substation node is for hosting transformers, and for each substation, they could have more than one transformer. And for substations, they have similarly they have different attributes which represent their locations and their names, etc. So it's very essential for us to find out the location of the substations, so then we can map them on the flooding regions to identify whether each substation would be affected by different types of flooding or not. And then we have circuit node, which has two ports for transporting power, so which could be an overhead line or cable. And for each circuit, we have lots of attributes as listed on the right-hand side. So in this diagram, each pink node, they represent a circuit. So circuit, they have name, their locations, their distance, and also the two bus bars they are connected to. And of course, we have other like parameters, resistance, reactance, capacity, etc. Because there are so many properties for each circuit. So we didn't show everything here on this diagram. And then we have a disconnector, so which is two ports for switching power. So similarly, each disconnector, they have different attributes, and they are represented by the pink node in this diagram. So I'm not going to discuss them in detail. And finally, we have circuit breaker, which is used for switching the fault current or high current or in the power system when there's a fault in the system. And similarly, we have lots of properties or attributes for each circuit breaker. And in this diagram, you can see that each green dot represents one circuit breaker. So relationships. So because we have so many nodes, and physically we know that each node that could be connected to each other, and also we have other relationship which is not physically like we have this relationship So our knowledge within our knowledge graph showing how different nodes or entities they are connected. So these relationships are crucial for understanding the context and the meaning of the data. So I have several key relationship types. So in total, we have 115,000 relationships. So many of them are they are like caused, like flooding is caused by something or has elevation, whether a substation has elevation data and also has impact, which means like if a failure has impact on another thing. So we have different types of these relationships to represent the connection of nodes, physical nodes, and also virtual nodes, which is like a flooding or some failure in the system. So So this slide describes two main types of queries we can normally perform on knowledge graphs. So first, we have these structural queries or SQ. So this focus on the connection between the nodes. So they search along the relationship without looking at the specific details or properties which node. Like we just concerned about the connection between different nodes or bus bars or substations. So we don't look at the details or where or the capacity of each node. So the result is a list of connected nodes and a relationship between them. For example, we find all the substations connect to a certain bus bar. So the second type of query is we call property query. So well, short name is PQ. So this focuses on the details within each node. So they search for specific properties like voltage levels or transformer capacity. So these queries often involve first finding each related node, and then so we check their properties. For example, find all the transformers with a capacity of 500 megawatts, for example, connect to a specific substation. So in general, as a rule, so queries searching for relationships between nodes are very efficient in graph database or in knowledge graph, but queries that search through large lists of properties within nodes tend to be less efficient. So here I did some demonstration here. So we can, once we have all the data together in the Neo4j, so we can do some queries to find the useful information we want. So for this slide, I shows we use Neo4j to count the total transformer number in the system. So you can see on the left-hand side, we have a small box. We have 3,085 transformer in the system. And on the right-hand, I have a circle, also circle, you can say. So they each dot represent a transformer. And then we want to visualize or find all the circuits like here because of the capacity limit of the computer. So we only visualize 500 circuits. So you can see we have root class in the middle, which is a class of circuit, and then we have 500 circuit. So we can see that the relationship is that all the circuits is the subclass of the root class. And then we can visualize all the substations. Again, so we just show the 500 substations, and in the middle you can see a yellow box, which is root class for the substations, and then we have 5 substations connect to this root substation. So their relationship is a subclass of this substation. And then, so quite interesting queries. We want to find devices or assets connect to a certain substation. For example, according to the NGET database, so we have a substation whose code is 840014. So we want to find all the devices, nodes or circuits or disconnectors or switch gears that connect to this substation. So we did this by using 10 hops. So you can see the substation is about here. And then by using 10 hops, so we can find all the devices connect to this substation. So we can find on the right-hand side, you can see we have found like 80 bus bars, 12 24 circuits and 20 disconnectors for 6 substations and also 28 circuit breakers. So we did another query. So we want to find all the substations. If we want to look a big space of each substation, how many devices are connected to them. So we use another substation. So the code is 89031. So we conduct 15 hops. So this substation is here. So if we use 15 hops, which means we jump 15 nodes, okay, so we can find all the devices connect to this substation. So we can see we have 12 substations, 114 bus bars, and also more transformers and circuit breakers and disconnect compared to previous query. So this is quite useful to find out the connectivity of the networks and how important each asset, like substation or circuit or node in the system, because we can easily find all the devices connect to them. And if there's a failure in one certain node, we can find all the potentially affected nodes by doing these hops. And then again, we can check the connectivities, also subclass and entities, for example, here. So we have 3 classes, which there are circuit, okay, we have disconnectors, and we have circuit breakers. So we can see they are connected to each other. So this is the root class for the 3 subclasses. So here, each dot represent here, they represent a circuit breaker. Here, each dot represent a disconnector, and here, each dot represent a circuit. And finally, so we want to, we added another node, which is elevation of the substations. We want to find out the elevation of all the substations above the sea level, which is very important or useful for finding out whether each substation can be affected by flooding. So we have the class here in the middle. So that's the elevation class, possibly a little bit hard to see. And then we have different elevation levels like this. I think it's like, I'll show you later, like a 1 to 10 meters, 10 to 50 meters. And for each elevation level, we have lots of substations within this level. So we can group all these substations together. So we can see we can have different levels of elevations, and we each region have different numbers of substations. So this is very useful for assessing the flooding risk for substations. And finally, so if we want to visualize the whole knowledge graph, so we talk about the bus bars, transformers, substations, circuit breakers, disconnectors, etc. So if we put all this information together, so we can have a beautiful diagram like this. Because the capacity of the software, so we only show 1,000 nodes. So okay, so all here, like for these 1,000 nodes, we have 453 node bus bar. Okay, we have 82 transformers, 131 circuits, and you can see we have 1,753 relationships within this diagram. So as said, it's very easy to identify any 2 assets or nodes that have connection or not, and what the relationship between them. So it is quite useful for us to analyze the impact or cascading impact in the power system. So the conclusion and the next step. So knowledge graphs are a very powerful way to bring different types of data and information together. So they excel at integrating heterogeneous data, meaning data from various sources, formats, and providing a unified view. However, the quality of knowledge graph directly depends on the quantity, also the quality of underlying data. So we see huge potential for knowledge graph in power system operation and maintenance. And one example is speeding up for example, the connection queue for system resources. So finally, so we can further enhance the capacity of knowledge graph by combining them with advanced technologies like deep learning. So allows for more sophisticated searches and applications. So that's my slides. So I would like to show you some or demonstrate some queries before the QA, if you like. Okay, so let's end my presentation. Can you see my screen?
Yes, we see it.
This is a Neo4j platform. So as we implement our knowledge graph in this platform, so you can see already uploaded the dataset from Engage system. So just let me show some queries. So first, like if we want to, use this Neo4j, possibly you are familiar with, so we can open up this browser. So hang on a minute. I'll bring it here because we don't need a database. It's loading. Okay, so then we are connected to the knowledge graph for the NGAD. So I want to find out the data schema for the knowledge graph we just developed. So we can run this query. So you can see, so we have the data schema for the knowledge graph. So we have 16 classes, and we have the relationship between each class. And you can just click each circle to find the detail of each class. Like here we have flood, and we have transformer, and we have substation. So that's how can we find out the data schema for the knowledge graph. And now I want to do a simple query on that we want to count the number of transformers. So you can hear, that's the total nodes in this whole knowledge graph because it's too huge, so it's not possible to visualize all of them. So I just want to count the number of transformers in this knowledge graph. So I can do this. So you can see it's the total number is 3,085 substation transformers, and now I want to visualize 1,000 of them. Okay. So visualize 3,000 might be too slow. So if you want to just visualize 1,000, so I got to this query, it will take a while. So you can see we can find all the substations. So each dot, 1,000 dots altogether, and each represent a transformer. So if you click one dot, you can find all the detail of this transformer. And I can repeat this for like circuit. So if we want to just visualize 500 circuit. Okay, here we go. So you can see again each dot represents a circuit. So and you can see their names here. Okay, so if you click one dot, you can see its attributes. Okay, all the details information here for the circuit. And just another example, if we want to visualize substations. So again, here I just show 500 substations. So it's a bit slow because the data set is very huge. Let's close this. Okay. So you can see all the substations. So you click one, you can find the details. Actually, you can move them around if you like, but it'll be very slow. It depends on the how powerful your computer is. And again, so if we want to, as I showed in my slides, if you want to connect all the devices can connect to a specific substation by using 10 hops. So we run this command. Then you can see all the devices connected. So we have the substation here, and I can find all the bus bars connect to this substation, and then circuit disconnect transformer they connect to each other, which are linked to this substation. So this is only by doing 10 hops. So if I want to increase the hops to 15, so you will see different results. So you can see that this substation here, and then we have 15 hops, so we can find all the devices related to this substation, and you can click each dot to find out their detailed properties. Okay, so and you can also move around, as we said. This to make this much clearer if you like. And then we also talk about the elevations of substations. So I want to visualize the elevation of our substations. So if I just make it a bit bigger, so we have elevation here. Just zoom in. So that's the elevation number through 300 to 400 and 400, 500, 0 to 100. So we can find out all the substations they are within each elevation level. And again, so we would like to visualize the whole node graph we just developed. And because of the capacity limit of the computer, I only visualize 1,000 nodes here. You can visualize all of them, but it's very, very slow. So that's the knowledge graph we have. So we have 1,000 nodes, and you can see we have how many bus bars we have, transformers, lines, and also we can find their relationships. Can make this a little bigger. Okay. So that's the knowledge graph we have for the 1,000 nodes and the relationships. Oops. Okay. So that's all. I think. Thank you so much. And of course, if you are very good at Cipher, for example, you can do lots of visualization or analysis by yourself. But as we say, we just did some preliminary work on this, and we are still working on this project. Thank you.
Thank you very much, Dr. Wu, for the interesting presentation. I highly encourage the audience to pose a question in the chat. In the meantime, we will start with questions from the studio here. So pardon my ignorance, but I will start with a semantic question. For people who are not expert in power system, could you define what the substation is, and for you, what it's important to characterize them and the connectivity between them?
Yeah. Yes. Yeah. But you needed the data from like system operators, so they publish all the data they have. Then you can connect them by finding the relationship between them. But in practice, because they publish data in way different locations in their website or in their database, so you need to do this manually to connect them, or you can need to write code to connect them. So then you can have this knowledge graph. Otherwise, you have data sets where they are isolated from each other because you don't have the relationship.
All right. So you're trying to recognize different information from different power stations to see how they interact between each other.
Yeah. Yeah.
Okay. Okay. I needed this clarification. So So let's move on to more like technical question then. So you mentioned several times that you have plenty of nodes and large number of relationships
Yeah.
in your knowledge graph. So my question would be, how scalable is this? And how many learning parameters are we talking, for instance, to handle national power system?
Sorry. So
So how scalable is your approach, and how many
okay.
parameters are we talking if we want to handle national power system?
Okay, yeah. If you look at the national system, I mean, the data might be a problem because you need the data, and to build a knowledge graph. So, I mean, if the company they don't publish, you cannot get the data. But if you have the data, you need to find the relationship between them, and then you can build a knowledge graph. If you want to make it for a larger system, and then I think the as long as your data and then the limit then is up to, I mean, is on the your the power whole capability of your knowledge graph tool. Like for this Neo4j, and if you want to use free version, I mean possibly okay. But if you have billions of nodes and relationships, and that could be for a big power system, for example, and then you need some kind of professional uh, version. I think that should be doable.
Okay, so all the application you show us are for which kind of size of power system, for instance?
So currently we are just focusing on distribution networks because they are more vulnerable to like flooding risks. But as we said, this knowledge graph is a fundamental tool, so which can be used for many applications. Like flooding risks is one, and also you can identify the connection queue. Like if because we have such a long queue for renewables to connect to the power systems, and then we have bottlenecks in the power system, and so this knowledge graph, they can easily, I mean, identify the what's the bottleneck in the system, and then we can speed up the connection by resolving the constraints or bottlenecks on each on certain node or in certain regions.
All right, very interesting. Hamid, do you have any question?
Yeah, absolutely. I can help with some of the questions. This is the role of the co-chair. So thank you, Professor Go, for the interesting talk. I really enjoyed the demo as well, which is something always risky to do live demo. So it takes like sometimes every time I do a live demo, I kind of like fail with my. So my question is about the users. So
Yeah.
who is the envisioned user of this tool? Like and in the kind of like in the time of there will be data at one day of billions of nodes. What would that user, how the user could process large outputs? So and aggregate this information and make decision at the end.
Yeah. I think that the immediate user would be the network system operators like National Grid Electricity Distribution, UK Power Networks, because they are managing all the devices, they are planning and operating the systems. So this tool will help them to identify the problem in the systems, what are the related locations to each site, so they can easily like resolve the problem they have in the system, and also they can identify the key assets in the system, so they can protect these assets properly, like for different kind of risks. So that's the preliminary, I think, use of this knowledge graph. I think possibly in the following years, once we have expanded capacity for knowledge graph, so it's quite useful for other third parties to use it. Like if you are a energy storage, or if you are a wind farm, you want to connect to the system, and you want to understanding what's the problem in the system, where can I connect my devices to. So this will help you to identify the best locations where the system has capacity, spare capacity, and you can connect which is less vulnerable to different risks, for example. So that would be, I mean, the second stage of application. But as we said, the Ofgem, they launched the like data sharing roadmap for the whole energy sector. I think as long as we have a lot of data information, we can put them together to build a fundamental knowledge graph for the power system. That could be, I mean, in the future, we can look into.
Fair enough. And you mentioned multiple times the flood risk. The environmental agency publish um, flood risk maps, and this is
Yeah,
somehow now is being used even by normal people who want to assess buying a home, or the
yeah,
insurance differently company takes that into account, and on a higher level than individuals, planning permits are this goes into effect. And in my mind, flood risk maps is geospatial data.
mm,
When you plotted the graphs here, my understanding that the graphs were plotted maybe using a graph layout
yeah,
techniques,
yeah,
string
exactly. Yeah.
fourth string things. It's not connected to geospatial. Is that something you are thinking of doing, or is that capability is available but not
Uh,
shown to us?
Yeah, very good question. Exactly. So we download all the elevation data from GIS platform. Like we use QGIS. So we have elevations, and then we download that, and then connect that data into the like knowledge graph we have here. So as you said, flooding is a big risk to the electrical power systems. But currently the problem is the flooding. Forecasting might be not good enough, so that's the risk for for us. So it's really about how to increase the prediction accuracy for different types of flooding, sea level or running flooding, etc. So I think that's maybe not a problem we can solve alone. I think we need to work across different disciplines.
And in terms of visualization, when you filter by height, is there a way to filter by height, but project the nodes on the map of the UK? Is that a capability? So we know if it's an isolated station next to shore, and then, or is it like something like a large region which could lead to cascading events of power failure?
Yeah. Yeah, exactly. So, once you have a problem in the system, so you can by identifying their connections, you can see which areas or regions are isolated to the main grid, and if they're isolated, possibly they could have a blackout, for example. So it's also very useful for the system operator to restore the power failures once there's a risk or blackout in the system to restore the power supply to customer as quickly as possible. So that's why I think it's a very useful tool for power system operation and maintenance.
Okay, thank you. I will add the banner here. We didn't have any questions so far. I can keep asking questions. And on my future research, I am always thinking of integration of knowledge graph with large language model with coding capability.
Yeah,
We can
yeah,
have a large language model generating the queries and just automate this
exactly.
within. Is that something you are currently doing, or you are, but you're not complete, or or this is will be the next talk?
Oh, that could be very challenging for us because we are not a computer scientists. But we are try to integrate the planning standards into knowledge graph because we have standards and they are in kind of way formatted way, so it's easy to use large language models to integrate these kind of standards into this knowledge graph. But in terms of queries, like as you suggest, might be, I don't know, maybe very difficult for us to develop at the moment.
Thank you, Sarah. The floor is
Yeah,
back to you.
yeah. I will also have like two more questions. So as my first one, we go back to the relationship types. So are these set up in advance or automatically learned during the process of constructing the graph?
Mm.
And if so, how? And would you be interested in learning sparse relationship types somehow instead of having like huge number of relationships, or do you want to explore how the potential risk?
You mean the sparse of the system?
Yeah, I mean sparse in terms of relationship types you can have between your nodes.
Uh, I mean, so in terms of sparse, normally when we solve the power system problems, we have sparse metrics. So it's very difficult to solve this kind of big matrix with lots of zeros in the matrix. And as I said, it's because if you have lots of zeros, it takes lots of memory to solve the problem. So for this knowledge graph, and as a power system, so it's very important to identify either we have isolated areas, regions, or nodes in the system. Because as we said, if they're isolated, there could be no power supply to them. So it's really about how to quickly and accurately identify these location regions. Like suppose you have flooding and the customer don't have power supply, and if you just rely on customer to call you, that could take a very long time. But if you can identify these random areas by this powerful tool, that could be very quick. And also the cascading effects, like this region is flooded or whatever, no power supply, how that consequence will propagate to other regions. And then you need this kind of connections, I would say.
Yeah. Yeah, that's not really what I meant. But so at some point you mentioned like having more than 100,000 relationship types for an example. So I was wondering, are these preset in advance, or how do you learn these relationship types?
Yes. So I mean, so you possibly want to divide these types relationship into different groups. So like some assets, they are connected to each other, so they have physical connections. And then you could have some virtual relationship, like flooding has an impact on substation. So that's the relationship should be defined by the users themselves. And if you have specific applications, you want to identify the nodes first, and then you want to identify or define the relationship between different nodes. So some physically, some should be like virtual relationships defined by the users themselves.
All right. And on like small example, do you know how interpretable has the automatic generation of knowledge graph compared to what an expert knowledge would put out there?
Yeah, so it's a difficult question. I think some people trying to use knowledge graph to enhance the explainability of machine learning models. I think that's the one way. So which means very important to build a fundamental knowledge graph by integrating like basic knowledge standards into the knowledge graph, and then we can explain some machine learning models by using this knowledge graph.
Okay. Thank you very much.
Yeah, thank you.
So we don't have any questions from the YouTube audience right now. So I think we will end up here. So thank you again, Dr. Wenghang Hu, for your presentation. We would like now to advertise a next session, which will be held next week and will feature two early research careers, Corentin Hooper from the University of Leicester and Alkan Loftipour from the University of Surrey. So thank you all for attending this session. Stay tuned for the next webinars, and thank you very much, Ahmed, as well, for sharing with me today.
Thank you much. Thank you.
Thank you.
Professor.
Bye.
Bye.
Bye.